Hi everyone, welcome to this channel. So today we are going to do text classification using NLP. The data that we'll be leveraging is from a hackathon that is currently running. So I'll just share my screen and we'll get started. Okay, so this is a hackathon that is currently ongoing. The objective of this particular hackathon is to categorize the reviews from different customers into different categories. And these are the different categories that are present. So one particular review is related to components of the product, one review is related to functionality of the product, and so on. So I've downloaded this particular data. I'll be sharing the data along with this particular hackathon link in the description below. Make sure to check that out. I'll also be sharing the complete notebook with all the codes. So this is the data that they have provided. So the train data that they have provided consists of multiple reviews from users. So this consists of different things like, for example, excellent ceiling fan brace, easy to install and well made. So this is regarding the installation process of that particular product, due to which the class installation is 1, whereas the remaining classes here are zeros. There are certain cases where like 2 different classes would be 1. There is one particular review can belong to multiple classes. And there is also a polarity. If we go to the right, we can see the polarity column. This is talking about whether the review is a positive review or a negative review. So easy to install, etc. These are keywords that that are identified as positive things. So this is termed as a positive review. So this is the train data that we have received. Now we'll go into the modeling right now. But before that, just wanted to outline the process that we are taking in order to do this particular text classification process. So the first thing is we look at the data, we do some exploratory data analysis. After we do our EDA steps, there is a data processing. So it is review. So it is a text data. So since it is text data from multiple customers, we would have to pre-process the data and clean it up. And finally, we'll go into different ML models and we'll pick the best model for different categories. So let's jump right into the code. Yes, yeah. So in the code itself, the first thing that is done is to import different packages by installing it. First of all, we'll be going through each of these packages down below. This is all importing a couple of packages that we are going to use. So firstly, I'm loading this particular data. After loading this data, we can see the data here. It's consisting of roughly 6,000 records in the training data, and we can see the 12 classes here. So components, delivery, and customer support, etc. Till the polarity. Now the test data that we are given consists of 2.6K rows, and this particular set of rows do not have any it does not have any classes populated. So we need to build a model in order to predict the categories for these texts. So we'll be doing that down below. So the first thing whenever we get any data is to do EDA. So the first thing that we looked at is distribution by length. So I have added IPY widgets, which make it very intuitive in order to see charts and other visualizations. So for example, here, the first thing that we are going to look at is the total number of words in each of the sentences, in each of the reviews. And we want to identify if it's a very long essay, like a paragraph review that is provided by the customer, or if it is like a 1 or 2 liners that is provided by the customer. Now, when we look at the review that we have received in our training data, we see that most of the reviews have a word count below 100. Like most of them are situated here. Like there are very few cases where the number of words in the review is going greater than 100. And we can look by different categories. That's the use of IPY widgets. We can just filter upon any single category, and this particular graph would just filter for that particular set of reviews under that category. Okay, now since we know that most of our reviews are below 100 words in length, we can actually think about how we'll represent these sentences in the form of a vector. We can use TF-IDF vectorizer, or even language models like BERT, etc., in order to get the embeddings out. So one thing that we are going to look at right now is the distribution of reviews. That is what percentage of the reviews are in each of the classes. So when we look at the polarity, we see that the average polarity across all the trained data examples that we have is 77%. That is 77% of the sentences in our trained data are positive reviews. The next EDA summary that we are going to look at is the overlap analysis. So overlap analysis is just to identify if it is a multi-class problem or a multi-label problem. Now, if it's a multi-label problem, then a single review can belong to multiple classes. So one same sentence may be under components, and the same sentence may be under quality as well, another class. And here, this particular highlighted portion shows the percentage of reviews under each of the classes which have an overlap with another class. So for the components class, 30% of the sentences which are classified under components are also classified under functionality, and 24% of the sentences classified under components are also classified under quality. So this is a multi-label problem. We need to build a multi-label model or even binary models. So since we have looked at the EDA analysis and we have confirmed that it's a multi-label problem, or that we can solve it through a binary modeling exercise for each individual category, we move on to the data processing stage. Now in the data processing stage, the first step is to look at the sentences if they are clean or not. To do that, we'll use several functions. We'll go through each of them below. So I've written specific functions in order to address certain things in the cleaning process. So the first thing that we are going to do is to remove redundant spaces. So redundant spaces as in, for example, in a sentence itself, for example, if I have a sentence like a pencil is placed space on the desk, we need to convert this particular sentence into this form where there are no redundant spaces. So in order to do that, we have a function right here. It's just a regex pattern. So this is doing that particular job. And we are also removing certain full stops. So there are certain sentences in our trained data which have multiple full stops. So it's like ... and then the next sentence begins. We don't want that. We want it in the form of single full stops like this. So that has been addressed here, removing multiple full stops. We are also correcting the spellings of certain words. In order to correct the spelling, one of the packages that we are using is PySpellChecker. So this particular function contains a dictionary of words in the English language, and from that it checks the spelling and then corrects the spelling of misspelled words. And as stated previously, all the code, the entire notebook would be present in the GitHub. So it will be present in the description below. Yes, the other pre-processing steps that we are doing is to break combined words. So there are certain sentences which have words that are joined together, like placed on the desk. And then the next sentence will start like this. The pencil was useful. So desk and this needs to be split. It needs to be split into desk space and the remaining part of the sentence. That is done using this particular function right here. So this is actually a regex pattern that I've written to fix the combined words. Once we do all of these pre-processing steps, we look at the sentence right now. Now, this is one particular sentence that I have taken. For example, if we look here, the review is, this is a below average camera. The only thing I can say is decent about it is that in comparison to the Cami doorbell on the APP, that this camera hasn't gone offline a million times, and so on. And we can see that there are certain spelling mistakes here. For example, keeps going offline with an M, and this has been corrected in the updated sentence. So this has all been done right now. Apart from these pre-processing steps, we are also utilizing a function known as clean text. So this particular function has a lot of parameters to do cleaning effortlessly. So we can just specify certain flags in this particular list of parameters, which will clean the text for us. And we are cleaning the review sentences for TF-IDF and for transformer embeddings. Now, why we are doing two types of cleaning is that we need not do certain types of cleaning for transformer models. For example, we need not remove stop words for transformer models because we want the context to be considered. We don't want to remove stop words or unnecessary things from the review for transformer because the context, the semantic meaning of the sentence is important there. But for TF-IDF vectorizer, those things are not important, due to which I'm removing punctuations, any phone numbers, any emails, line breaks, etc. We are removing, we are lowercasing it, etc. But for the cleaning for the transformer embeddings, we are not doing that. We are only doing a couple of steps. We are not removing punctuation. We are not even removing stop words, etc. Now, the next step is to lematize or stem the sentence. Now, in order to stem it, there are multiple options available. One particular option is a Porter stemmer. So we can decide to do a stemming operation or a lemmatizing operation and see the increase in performance for modeling. Right now, I have done lemmatization, where the base word or the lemma of a word is identified, and then we get the sentence out. Yeah. So after all of these steps, we have the complete sentence here. So for example, for this input sentence, yellow sprinkler made from pretty thin plastic, although that doesn't stop it from being sturdy and seemingly tough, and so on. This is the complete sentence right now. You can see that everything is in lowercase. We have removed certain punctuations from here. So this is how we want the TF-IDF vectorizer to take the sentence. So we'll start off with one particular class. So in our Excel, we saw there are multiple classes. I believe there are roughly, there are 12 classes. Now we are going to do this particular modeling for one of the classes. So we are doing it for the quality, that is this particular column right here. And it can be, this entire notebook is reproducible for any other class. We just need to change the column name from quality to any other column name. So I've just run this notebook for a quality class. I've added certain helper functions, etc., in order to get the classification results out. Okay. So one of the things that we need to identify is how to represent a sentence in a vector format. So the first thing that we have done right here is to get the embeddings from a language model. One model that we have taken is a BERT-based uncased model. If you are new to NLP, do check transformers out. Once you understand transformers, you can understand what produces. So for example, the BERT-based case model, it takes a sentence and it provides the embedding of that particular sentence, basically the meaning of that sentence. So the output from the BERT-based uncased is a list of tokens, and we have taken the CLS token, that is the first token from that particular model, which consists of 768 embeddings. So these are the 768 columns that you see. So for every review, every row, we converted that particular row into 768 components. This is the vector format. Now this is the vectorized format using transformers. You can also do this using TF-IDF vectorizer. Now to do TF-IDF vectorizer, we use the TF-IDF vectorizer function. We give a list of stop words from English, and we are only considering unigrams here. Now, once we do the TF-IDF vectorizer, you can see the data here. So for example, if I run it, and if I do a head, you'll be able to see the different words and the shape of the data frame. So this particular data frame, just by using unigrams from TF-IDF, consists of roughly 6,000 columns, which is huge. So we can't like provide all the 6,000 columns for modeling. We need to reduce the dimensionality so that the modeling gives a good performance. To reduce the dimensionality, there are multiple methods out there. One of the method is PCA. Alternatives include like UMAP, TSNE, etc. Even autoencoders can be used. So I've right now done a PCA over this particular train data. So we take the 6,000 columns and we convert these 6,000 columns. We reduce it to a list of 2,000 columns. And how to identify that whether to drop it down to 2,000 or whether to drop it down to 1,000 and so on. In order to identify that, we can look at the scree plot. So this is basically the scree plot. What the scree plot tells us is that at what number of features would my percentage of variance captured be very high. So for example, if we look at this particular chart, we see that at 2000, it's covering more than 90% of the variance in the train data, which is very, very good. Like 80% of the variance is covered at roughly 1,100. So at 1,100 number of features, we get 80% of the variance covered. So I'm taking 2000 right now for this particular analysis. And I have transformed all the columns right here. So you can see that there are 2,000 columns. Now the 6,000 columns that we had from TF-IDF is now converted into 2,000 columns. I've also split the data into train data and validation. So we'll be training the model using our train data. We'll be testing the model out on the validation data. And I've also ensured that the target balance remains the same. So 35% of the reviews in the train data are related to quality. And similarly, 35% of the reviews in validation data are also related to quality. We can do a consistent train test split using this particular parameter, which is stratified. So once we create the train data and the validation data, we are going to run multiple ML models on top of this particular process data. Now, the first thing that we do is to generate a base performance. So to generate a base performance, we have chosen a simple model. There is a logistic regression model. Now, from the logistic regression model, we have run the logistic regression model on the train data, and we are seeing a binary cross entropy of 0.40516 on the validation data. And we also have the ROC curve, the receiver operating characteristics, which gives the curve between sensitivity and the false positive rate. And it has a good AUC rate here. So it's actually performing quite well, like a 77% F1 score on the validation data with 88% F1 score on the train data. So it's not overfitting too. Now we go into other ML models. One other ML model that we tried is a support vector machine. So in support vector machine, we are getting a higher log loss. So the log loss that we are getting is 0.498, which is higher than what we received in logistic regression. So this is working poorly compared to logistic regression. Apart from that, we have also tried gradient boosting methods. So gradient boosting methods are of multiple types. There are multiple models available like LightGBM, CatBoost, XGBoost, etc. We have used XGBoost right now here. And right now, the XGBoost parameters, the best parameters for the model is identified through Optuna. Now, Optuna is a hyperparameter optimization framework that will give us the best parameters for a model. Now, in order to do that, we have defined a function called objective classification, which takes in our train data, validation data, and so on. And it generates a list of possible combinations of the hyperparameters. Like, for example, the boosting list can be a gradient boosting tree or a GB linear function. The number of trees that are fit in XGBoost, it may be, it's ranging from 20 to 200. The maximum depth is ranging from 2 to 16 and so on. So Optuna allows us this particular functionality to set the parameters between a range, and it identifies the best parameters based upon a score. So the score that we use for Optuna to identify the best hyperparameters for the model is the ROC-EUC area. So it's the area under the ROC curve. So greater the area under the ROC curve, the model is functioning better. Okay. Yeah. One other thing that we have applied on before doing XGBoost is to select relevant features. So in the train data, we had roughly 6,000 columns. Now we are not doing PCA here. We are taking the 6,000 columns directly and selecting only the useful features from that 6,000 based upon a function called BoostAroota. So BoostAroota, what it does is it actually trains XGBoost models, and then it identifies the best features for the XGBoost model from the list of features that are provided to it. How it does so is based upon creating shallow features and identifying the number of hits, etc. You can read about you can read about articles upon BoostAroota in order to identify how it actually works. It identifies the number of hits given to each variable and identifies how important it is. That's how it selects the total number of features for modeling. So here we have applied BoostAroota, and then we have applied Optuna over the features coming from BoostAroota. And inside Optuna, we are training a XGBoost model, getting the best parameters out, and then creating a classifier here, XGBoost classifier, with the best hyperparameters from Optuna. Now, once we run this particular cell, we see that the total number of features for modeling before BoostAroota was roughly 6,000. Once we run BoostAroota, the number of features reduces drastically. So the total number of features for modeling after BoostAroota is roughly 200. So 6,000 has reduced to 200 just by using BoostAroota. And when, so Optuna has trained the XGBoost model and identified the best hyperparameters. So it basically does different trials. Basically, it assigns the maximum depth and other hyperparameters between different ranges and identifies the best set of hyperparameters, which will give the maximum ROC, area under curve. So for this particular XGBoost model that we have trained, we have the performance below as well. Yes. So for this particular XGBoost model, this model is working really well. It's providing a F1 score of 80% on the validation data and at 87% on the train data, which is really good. And a cross entropy of 0.4303 on the validation data. Now, in order to see the features that are important for this class quality, we have used SHAP plots. Now, SHAP plot just provides which are the important features that the model uses in order to identify whether a sentence is belonging to a class or not. Now, for the quality class, it is very intuitive to understand that the quality keyword in a sentence makes the model understand that this particular sentence is related to quality. The red points right here indicate that there is a high value for the feature. So the feature quality, that particular column has a high TF-IDF value, due to which it is colored in red. And since it is red, it's also towards the right. That means it's having a positive impact on the model output. That is, it is pushing the model predicted probability upwards. So if the quality word is present in a review, then the model is more sure that the review is about quality of the product. And there are different types of SHAP plots that we can do. We have a waterfall plot, we have a force plot, and so on. So this, what you are seeing right here, is a waterfall plot. So from the base value of 1.032, it identifies how it achieves the final value of minus 0.642. So these are log odds. These are not predicted probabilities. That's why it's going above 1 and so on. This is the force plot from the SHAP plot too. So we can identify like which are the features that are increasing the probability. So these features are pushing the probability towards the right, that is, it is increasing. Whereas these features are pushing the probability towards the left, that is, it's decreasing. So we have the performance from the XGBoost model. We saw it was giving 80% F1 score on the validation data. Now we are going to try an AutoML approach. Now, an AutoML approach fits multiple ML models on our trained data and identifies the best model from a cohort. Now, in order to do AutoML, there are multiple functions available. There is eval-ML. There are AutoML packages in sklearn. There are also AutoML packages from H2O.ai. So I've used H2O.ai AutoML process. I've used the TF-IDF vectorizer only. And I have selected mainly 500 columns here. So 500 columns when selected reduces the complexity, and it still captures 70% of the variance. So that's why I've selected 500 principal components. Now, after converting the data frame from 6,000 to 500 features, I'm fitting the H2O AutoML on my data frame. And once I do that, I get the performance of multiple models that are trained by H2O.AutoML. And I get the area under the ROC curve. I also get the log loss. So I can see a log loss of 0.35 from the best model coming from the AutoML approach. And this is the lowest log loss that we have seen across all the models that we have trained. So we have trained basically 4 models right now. So I have like consolidated all the results from our modeling approach into this particular Excel. You can see the best approach that we have is the H2O.AutoML approach. In this particular approach, we are getting the lowest log loss for this particular class, that is quality, log loss of only 0.35. So this is how we do text classification in order to classify the text into different categories. We can just do this particular process once more for any other category, and we'll get the test data with the category. So for example, if we look at the test data right now, actually the submission data, we can see the result. So for different IDs right here, for different sentences, we have the probability that that particular sentence, that particular review is under quality or not. So 58% probability that it's under quality, 9.6% probability that it is under quality, and so on. So this is how we do text-based classification using NLP. We have trained multiple models. There are other models that we are yet to train. Stay tuned for another update upon this particular classification approach. I'll be sharing multiple other approaches and adding to the GitHub repository, so you can go right there and see the best models. Thanks for watching. Please do subscribe for more code overviews and data science concepts.